There's a lot of content out there on how to pick the right target storm, but there's not a lot of content out there on how to navigate safely and effectively around that target storm. What do we mean by navigation? It's how you interact with a storm, what routes you're taking to maneuver around a storm and its hazards, how close you're getting to those hazards, etc. And there are several factors that modulate how you should navigate around a storm. The first is your storm chasing goals. If you're interested in getting photography of the entire storm, if you're looking to get time lapse, or if you're just looking to experience the entire storm structure, then you may want to set up farther back from the storm. If you're out there to see tornadoes, to experience their raw power, or you're just into it for the adrenaline that gives you, then you may want to be a little bit more up close. Every storm chaser is going to have different goals that they want to achieve with their storm chasing, and therefore everybody's going to have different areas relative to the storm where they feel the most comfortable and where they feel is going to be the most effective for achieving those goals. This goes hand in hand with your comfort and skill level. All storm chasers, no matter your storm chasing goals, whether you want to get close, whether you want to stay farther away, all storm chasers need to have good knowledge of things like storm features, storm processes, how to read radar, mesoanalysis, etc. But if you're going to get up close to tornadoes, you need to have an especially good understanding of these things, particularly storm features and processes. This is not going to tell you to never get close. We're going to teach you how to do so safely, but you are responsible for your own actions out there, and you need to have a good understanding of your own skill level and your comfort level. If you're a newer chaser, maybe you haven't really chased before at all, or you don't have a great understanding of things like storm processes and storm features, then maybe getting super close is not the best idea right off the bat until you're more experienced. And if you find yourself in a dicey situation out in the field that you're not completely comfortable with, it's always okay to back out and stay farther back. There will always be more storms and tornadoes. One storm getting one spectacular photograph or video is not worth your life. Another major factor is the type of storm that you're chasing and the environment that it's in. The way you interact with a high precipitation supercell is oftentimes going to be a lot different than the way you interact with a low precipitation supercell. Different types of storms have different ways that you are best going to be able to interact with their hazards. So that should be a significant factor in your decision making during the navigation process when chasing. Also, the environment that the storm is in. Is it an environment that may favor strong to violent tornadoes? You might want to back off a little bit in those cases. Stuff like that. Also, where you are has a big impact on how you should navigate. What's the road network where you're chasing? Does it have gridded roads? Does it have just a few roads here and there of questionable quality? Is the terrain hilly? Does it have a lot of trees, or is it more wide open? And the traffic on the roads. Is chaser convergence high around your storm? Are you in or near a major metro area? These are all very critical factors in navigation for storm chasing.
Additional seats have been added for our 2027 Storm Chasing Tour. Link in the description.
So what are the must-haves for effective navigation? As we talked about just a minute ago, you need to have a good knowledge of severe storms meteorology, storm processes and behaviors, etc. Things like what different storm features mean, how to read radar, mesoanalysis data, etc. You need to have a well-rounded knowledge of all of these things if you're going to chase in any capacity, whether you like to get up close or you like to stay farther away. A well-rounded knowledge of severe storms meteorology is critical for effective storm chasing. You need a good, reliable vehicle. You shouldn't be out there in a car that you're not sure if it's going to be able to get you home that night. The last thing you want is the check engine light to come on when you're right in front of a beastly supercell. You need to have good tires. If you're navigating in and around a storm, you're going to encounter some hostile conditions, some rain, maybe some hail. You might be on some more questionable back roads. So if your car's tires are bald, that's not a great idea for storm chasing. You don't need a four-wheel drive or an all-wheel drive vehicle. I chased in a 2013 Honda Civic for over a decade, and it served me really well. You just need a good, reliable car that's going to get you from point A to point B effectively and safely. Will a four-wheel drive or all-wheel drive vehicle help you out if you're on some of those dirt back roads that may have been exposed to a little bit of rain? Sure, but that's going to be a fairly low percentage of the roads you're traveling on when storm chasing, and maybe you're someone who doesn't like to travel on dirt roads. That's totally fine as well. In that case, and really in most cases in storm chasing, a normal vehicle doesn't have to be four-wheel drive or all-wheel drive, is totally fine. You just need a good, reliable car that's going to safely and effectively allow you to navigate in the hostile conditions that storm chasing presents. And finally, you need good navigational tools. We're going to have a full episode on all of those tools, things like Google Maps, paper maps, etc., the pros and cons of each. Whichever ones you choose, you need to have good navigational tools that you can use at all times, and it's often good to have more than one navigational tool. There are so many apps out there that have maps that will help you in that regard when you're storm chasing. It's always good to have multiple sources of navigational information when you're out in the field. Let's go over the three main types of supercells, including their visual and radar characteristics. Starting with the classic supercell. Classic supercells tend to have a flat, rain-free updraft base that is displaced from and adjacent to the heavy rain and hail of the downdraft. In this example, notice how the robust precipitation core with heavy rain and hail is off to the right, and the rain-free updraft base, which includes a nice wall cloud, is displaced from it to the left. In most classic supercells, the area of interest underneath the updraft base, which is often comprised of a rotating wall cloud, which is a manifestation of the low-level mesocyclone or rotating updraft, will be clearly visible and not obscured by much precipitation. Rotating wall clouds are often the precursor to tornadogenesis, so any tornadic activity with classic supercells is often quite visible as well. On radar, a classic supercell will often have a fairly clean appearance, so to speak. Features will often be fairly well defined, such as a hook echo and precipitation core, although not all the time. And just for some context, the updraft of the storm is located in the rain-free region within the inflow notch of the storm. So you can see clearly how the updraft is displaced from the heavy rain and hail of the precipitation core. Low precipitation or LP supercells often have a barber pole or corkscrew looking updraft with very little precipitation. Any precipitation that does fall is either transparent or shunted well away from the updraft of the storm. LP supercells are often quite photogenic. An LP supercell's updraft is located at the very rear flank of the storm, giving it that barber pole or corkscrew appearance. And oftentimes you will just see the barber pole updraft with very little, if any, visible precipitation. However, LP supercells are known for producing large to very large hail, albeit quite sporadic. Tornado potential is often decreased with LP supercells because of a less robust downdraft to balance out the storm's inflow, but LP supercells can still produce tornadoes on rare occasion. LP supercells often look fairly benign on radar with oftentimes much lower reflectivity values than, say, a classic supercell because of the overall lack of precipitation. However, again, that doesn't mean that the storm is not producing large hail, it's just a lot more sporadic. In most cases, LP supercells will not display a hook echo, but on rare occasion they can. The updraft of an LP supercell is located here, closer to the rear flank of the storm, giving it that exposed appearance. High precipitation or HP supercells are quite different. In an HP supercell, heavy rain and hail shrouds much of the updraft and the important features that are often quite visible in low precipitation and classic supercells, such as wall clouds and tornadic activity, making them very difficult to chase. HP supercells are often quite spectacular visually, perhaps with some striations or even a full shelf cloud spanning the entire leading edge of the storm, followed by lots of precipitation. All these grays, blues, and greens back here are heavy rain and hail. Tucked back inside all of that precipitation is where your tornadic activity might be. In some cases, you may actually be able to briefly pick out important storm features, such as in this example. This lowered area back in here is your low-level mesocyclone. All that inflow is feeding into that low-level mesocyclone, but you can see just how shrouded in precipitation that area is, which can make it difficult to tell what's going on back there. On radar, HP supercells often take on more of a kidney bean shape appearance due to the abundance of precipitation. Much of that precipitation makes the hook echo indiscernible, and the inflow notch that tends to be clean in more classic supercells often gets obscured by precipitation as well, giving way to the kidney bean shape. Sometimes you may still be able to make out the hook echo in an HP supercell, as in this example. If you follow the higher reflectivity values, you can trace out the location of the hook echo. This weak reflectivity hole right there is actually an ongoing strong tornado, but notice how much precipitation has wrapped around that tornadic circulation, which is a classic sign of a high precipitation supercell. The type of supercell you might expect to see in a given event can be forecasted ahead of time using atmospheric soundings. If you're looking through the models in the days leading up to an event, you might select a few forecast soundings in the potential area of interest to get an idea of what type of supercell you might expect to see. And this can give you at least a decent idea of how you might want to attack navigation during the chase. The diagram you see on the left here is the skew T. This shows you the thermodynamic properties of the atmosphere. And the diagram on the right here is the hodograph. And this is what we're going to hone in on when we're trying to assess the type of supercell that we might expect to see in a given event. The hodograph is a visualization of the wind profile in the atmosphere. The wind direction and speed is plotted at every single level of the atmosphere, and the dots are connected to give you a graph that shows you how the winds are changing as you go up in the atmosphere. Each point has a speed and direction. So our origin is here, and all of these rings that you see here, those indicate the speed of the wind in knots. So for example, let's take this point right here. This would be our point at 1 kilometer. You see the 1 right there. That indicates the altitude of that particular wind vector in the atmosphere. So our 1 kilometer wind vector would look something like this. So the wind at 1 kilometer is out of the southwest, so we have a southwesterly wind at 10, 20, 30, 40, almost 50 knots. So this is approximately a 50-knot wind out of the southwest. How about our surface wind? This 0 point here, that is our surface wind. So let's draw our vector up from the origin. Would look something like that. So our surface wind is out of the south, so a southerly wind at 10, 20 knots. So our surface wind is a southerly wind at 20 knots. The type of supercell that might dominate a given environment depends on the mid and upper level storm relative winds. These modulate how precipitation is vented relative to the location of the updraft. In other words, is the precipitation pushed far away from the updraft, or does it remain fairly near the updraft? This all depends on the storm relative winds in the mid and upper levels of the atmosphere. First of all, what do we mean by storm relative? Storm relative winds are just the winds with the storm motion factored out. So it's the wind that the storm is feeling. We're experiencing the winds from the storm's perspective. All we do to find that on the hodograph is, instead of drawing our wind vector from the origin, we would draw it from the storm motion to the point on the hodograph of interest. Our storm motion is given by this black bullseye right here. This is the bunker's right-moving supercell storm motion. It's not always a perfect estimate, but it's a good enough estimate for our purposes when employing these techniques. So for example, our storm relative wind at, let's say, 9 kilometers, this point right here, we would draw our vector from the storm motion all the way up to 9 kilometers. And it can be a little bit tricky because we're not at the origin here, so we might be a little bit offset from our actual rings, but just eyeball it. So where you start would be 0. This would be about 10, 20, 30, 40, 50, about 60 knots there. So our storm relative wind at 9 kilometers is out of the southwest, so southwesterly, at about 60 knots. For this technique, we're looking at the winds above 6 kilometers off the surface. If the majority of the storm relative winds above 6 kilometers are greater than 40 knots, low precipitation supercells will be favored because those stronger winds aloft are venting the precipitation much farther away from the updraft, making the updraft and its features much more visible. If the majority of storm relative winds above 6 kilometers are less than 20 knots, high precipitation supercells will be favored. In this case, precipitation venting will be quite poor, and therefore a lot of precipitation may shroud the updraft and its features. And if storm relative winds above 6 kilometers are between 20 and 40 knots, then you'll have a tendency toward more classic supercells, although it can depend on some other factors. In this example here, if we were to draw in vectors from our bunker's right storm motion to all of our points above 6 kilometers on the hodograph, you'll notice that they're all above about 40 knots. Again, you kind of just have to eyeball this because the bunker's right storm motion is not our actual origin, but you can just estimate it based on the spacing between each of these rings. So for example, this is our 6 kilometer vector. This is about 10, 20, 30, about 40 knots or so, maybe just over 40 knots. The 7 kilometer point is right on top of the 6. Our 8 kilometer vector, just a little bit longer than that 6 kilometer vector, so maybe about 50 knots or so. And then we've already figured out the 9 kilometer point, which is 60 knots. So all of our points above 6 kilometers are well over 40 knots, indicating that this profile would be very favorable for low precipitation supercells. Contrast that with this example here. Notice how truncated the hodograph is in the mid and upper levels of the atmosphere. If we were to draw in our vectors for our points above 6 kilometers, notice how short they are. Here's our 6 kilometer vector, this one on the right. It's maybe about 10, maybe just under 20 knots there. The 7 kilometer vector right there, even shorter. 8 kilometers, about the same as 6. And so all of these are right about 20 knots or below, indicating that this profile would be favorable for more high precipitation supercells. The shape of the hodograph and the configuration of the winds aloft also modulates how precipitation is vented away from an updraft. This is where veering and backing of the winds come in. Veering means that the winds turn in a clockwise direction with height, whereas backing is when the winds turn in a counterclockwise fashion with height. Because the configuration of the winds aloft modulates the dispersion of precipitation within a supercell, the hodograph is actually going to be a pretty good proxy for the shape of a supercell on radar, and it can give us an idea of the direction that precipitation will be vented relative to the updraft. In this example, notice how the winds veer in the low levels, but then they eventually back a little bit above 3 kilometers. Again, veering of the winds with height, those winds are turning in a clockwise direction in that lowest kilometer or two, and then they turn in a counterclockwise direction above about 3 kilometers. In other words, the hodograph bends back to the left a little bit. Now let's draw in a hypothetical supercell that matches this wind profile. So in the low levels would be our hook echo, our mesocyclone region of the storm. And above that, we would just track along the shape of the hodograph to see where precipitation would be vented. So to start, we would veer off to the right a little bit, and then once that backing occurs above about 3 kilometers, we would turn back to the north a little bit. And that shows us that most of the precipitation is going to be vented away from the updraft of the storm. Here is your mesocyclone. Tornadic activity would be located at that tip of the hook echo, and most of that precipitation will be vented away from that area, making the updraft much more visible and any tornadic activity easier to spot, and the storm may take on more of a low precipitation appearance. Let's do the same thing for this hodograph. Notice in this case that the winds just veer the entire way up through the atmosphere. They're turning in a clockwise direction in general, all the way up through the atmosphere. The hodograph is essentially folding over on itself. If we were to draw in our hypothetical supercell here, notice how the precipitation is vented out in front of the mesocyclone region of the storm. Here's your hook echo. Any tornadic activity would be here, and all that precipitation is thrown out ahead of the storm and ahead of the storm's motion, which is to the northeast, potentially shrouding the updraft in more precipitation and making any tornadic activity more difficult to spot. This lends itself to more high precipitation supercell structure. Now, there is one exception to these rules, and that is the mini supercell. Mini supercells are just smaller versions of full-fledged supercells. They have the same type of structure, same hazards, but they're just smaller in size. Mini supercells by nature don't produce as much precipitation. Therefore, if you have an environment that might at first glance suggest more high precipitation supercells, if the environment also favors mini supercells, that might not actually come to fruition. The storm relative winds in the lowest kilometer of the atmosphere modulate supercell size. This is called storm relative inflow. Storm relative inflow determines how much mass is flowing into a storm. Stronger storm relative inflow means that more mass is getting pulled into the storm, and therefore that storm is likely to be larger, whereas weaker storm relative inflow means less mass getting pulled into the storm, and you get a smaller storm. A general rule of thumb is that if storm relative inflow in the 0 to 1 kilometer layer is less than 25 knots, then mini supercells will be favored. In this example, if we were to draw in our storm relative wind vectors at the 0 and 1 kilometer point, for example, you'll notice how short they are. We can actually get a direct measurement For the surface storm relative wind vector, because the surface wind is right there at the origin, it's not even 15 knots. The 1 kilometer vector is a little bit longer, maybe about 25 knots or so. Both of those are underneath that threshold for mini supercells, and therefore this would be an environment that would favor mini supercells. Now, at first glance, you might think that this environment would favor high precipitation supercells. I've drawn in our 6 and 8 kilometer storm relative wind vectors, and they're very, very short, especially that 8 kilometer vector, which is not even 20 knots. But because we have such weak storm relative inflow, high precipitation supercells may be precluded because mini supercells are favored, and again, mini supercells produce less precipitation by nature. And while an environment may have weak storm relative inflow, we need to make sure that supercells are favored altogether. That usually means either 0 to 6 kilometer shear or effective bulk shear is about 30 knots or greater. And really this goes for all of the supercell types. Of course, we need to make sure that we have a supercell favorable environment in the first place before making these assumptions about supercell type.
We just opened up additional seats for our 2027 Storm Chasing Tour, and they aren't going to last for very long. The first round of seats sold out within 5 days, and considering the coaches who will be leading this trip and the unbeatable price tag, I expect these to move even faster. Link in the description for more information.
Now, there are some other factors that modulate the type of supercell you might see in a given environment. The first is the strength of any remnant capping in the atmosphere. The cap is a layer of warm air aloft that can inhibit the strength of updrafts. On a skew T diagram, that left portion of the sounding, you can identify a capping inversion by the warm nose that is present in the red line here. This red line is the atmospheric temperature as you go up in the atmosphere. The green line is the dew point as you go up in the atmosphere. So anytime you see a warm nose like this, where the temperature profile kind of juts out to the right like that, that is a sign of a capping inversion in the atmosphere. In some cases, this capping inversion may prevent storms from firing altogether, but sometimes you may have enough large-scale forcing to allow storms to initiate in the environment despite the capping, but that remnant capping can actually constrict the size of storms, allowing them to struggle a little bit and perhaps take on more low precipitation type characteristics. Another modulating factor is atmospheric moisture content. Intuitively, environments with high moisture content tend to favor more high precipitation supercells, whereas drier environments tend to favor more classic or low precipitation supercells. A skew T diagram can also be quite helpful in assessing atmospheric moisture content. In this example, notice how close the red temperature profile and green dew point profile are throughout pretty much the entire atmosphere. This indicates a quite saturated, moist environment favorable for high precipitation supercells. In contrast, this is a much drier environment, especially in the low to mid levels of the atmosphere. Notice how much separation there is between the red temperature profile and the green dew point profile in that layer. That indicates drier air and a tendency toward more low precipitation or classic supercells. On a sounding, you'll also find some parameters that can tell you how much moisture there is in the environment, namely precipitable water. Precipitable water is essentially the depth of water there is in a column of the atmosphere if all of that water were to be precipitated out as rain. The higher the precipitable water value, the more moisture there is in the environment. A very general rule of thumb is that high precipitation supercells are favored when precipitable water values exceed 1.75 inches, whereas low precipitation supercells are favored if precipitable water is below 1 inch. And in that middle range there between the two, classic supercells tend to be favored. Now, this is just one tool in a broader toolbox of techniques you can use to forecast supercell type. Just because precipitable water may be above 1.75 inches does not mean that you're automatically going to get high precipitation supercells. The precipitation venting via the wind profile aloft is often much more important of a factor, but the moisture content in the atmosphere can also display some utility when you're forecasting storm type. It's important to note that supercells can undergo changes in their type throughout their life cycle. For example, a supercell may start out as more of a low precipitation or classic supercell and transition into more of a high precipitation supercell with time. On the other hand, a classic supercell may run into an environment with slightly stronger capping, eventually turning into more of a low precipitation supercell toward the end of its life. Alright, let's go through a few examples here to reinforce the concepts that we've discussed in this video. We're going to look at a few different observed soundings from different cases. Normally, you'd be going through these techniques when looking at forecast soundings on the models in the lead up to an event, but based on what I had available, we're going to look at observed soundings here. The techniques are going to be exactly the same whether you're looking at a forecast sounding or an observed sounding. Let's start off with this first case here, and the first thing I would do is go right to the hodograph. See how precipitation would be vented around any hypothetical supercells in this environment. Let's start off with our mid and upper level storm relative winds. I'll draw in our vectors here. Here is the vector at 6 kilometers. The 7 kilometer point is right on top of the 6 kilometer point. And just estimating that be about 10, 20, just over 30 knots or so at 6 kilometers. If we do our point at 8 kilometers, it'd be about 40 knots or so. And then our 9 kilometer vector would be about 50 knots. So we have fairly strong mid and upper level storm relative winds increasing as we go up above 6 kilometers. And notice how the hodograph doesn't really fold over on itself really severely. We have a little bit of backing there at about 2 kilometers, which should help to vent precipitation, at least keep it away from the mesocyclone region of the storm. So overall, our wind profile is suggesting that we may favor more of a classic to possibly even slightly low precipitation supercell mode. Now looking at our skew T, we don't have a super moist environment. There's some drier air aloft, and precipitable water values are just under 1.5 inches. So all in all, with all those factors combined, it appears that this environment would favor more classic to maybe slightly low precipitation supercells. Overall, your important features, including any tornadic activity, would be quite visible. And this is actually the environment near the December 10th, 2021 quad-state tornadic supercell that spawned multiple intense EF4s that tracked through northeast Arkansas into Kentucky, producing damage in places like Monette, Arkansas, and Mayfield, Kentucky. The tornadoes were quite visible in this event, which corroborates our analysis and suggests that storms were much more of the classic variety. Moving on to our second example, and this one is pretty clear. You'll notice we have a very elongated hodograph in the mid and upper levels of the atmosphere, drawing in our storm relative wind vectors above 6 kilometers, and you can see that they are quite lengthy, especially that 8 and 9 kilometer vector, well in excess of that 40 knot threshold for LP supercells. That 6 kilometer vector, only about 25 to 30 knots or so, but above that, a deep layer of storm relative winds in excess of 40 knots. And we shouldn't have any issues with precipitation being shunted ahead of the storm motion and the mesocyclone region of the storm. If we do our technique drawing in the supercell shape around the hodograph, you'll see that all that precipitation should be vented well away from the mesocyclone region of the storm. So our wind profile certainly suggests that low precipitation supercells will be favored in this environment. We also have a fairly dry environment, lots of dry air above about 850 millibars or so, precipitable water values below 1 inch, and we have a little bit of capping to work with, a little bit of a warm nose there. All of these signs point to a low precipitation storm mode. And sure enough, this was a proximity sounding to a beautifully sculpted LP supercell near Dora, New Mexico that actually produced a tornado on May 26, 2019. How about this one? Let's draw in our vectors. Here's the 6 kilometer vector, and you see the 7, 8, and 9 kilometer points are really on top of each other there. And these vectors are certainly on the shorter side, maybe at most 20 to 25 knots, which is between those 20 and 40 knot thresholds, but definitely on the weaker side. We also see that the precipitation may tend to get vented out ahead of the storm's motion and ahead of the mesocyclone there, as the mid and upper portion of the hodograph is kind of folding over on itself, giving it that semicircle type shape. So if we were to do our little technique here, here's your supercell hook echo, and then the precipitation venting, it's going to look something like that. So we may get some of that precip vented out ahead of the mesocyclone of the storm, leading to a little bit more questionable visibility for any tornadic activity. Taking a look at our skew T, we have a pretty moist environment, especially below about 500 millibars there. Very deep, low-level moisture you see up to about 750 millibars. The red temperature profile and the green dew point profile are very close to one another beneath that very subtle capping inversion there. And then we continue that moisture up above that little inversion right there, just below 500 millibars. Our precipitable water value is about 1.64, so not above that 1.75 inch threshold, but certainly getting close. So a pretty moist environment, a fairly weak storm relative wind profile aloft, and somewhat poor precipitation venting relative to the mesocyclone region of any hypothetical supercells make me think that this environment might at least lean a little bit more toward high precipitation supercells. Maybe somewhat of a hybrid between classic and high precipitation, but leaning toward higher precipitation storms. And this was a proximity sounding for the Elmer, Oklahoma significant tornadic supercell on May 16, 2015. The tornado was somewhat visible for a good portion of its life, but it did get quite shrouded in rain at times. So we were kind of right on the edge between classic and high precipitation supercells with a little bit of a tilt toward a high precipitation mode. In this example, my eyes are drawn right away to the low-level storm relative winds, or the storm relative inflow. If we were to draw our vectors from the storm motion to the low levels of the hodograph, the surface vector is perhaps just a little bit over 25 knots, but as you get closer to 1 kilometer, that vector shortens a little bit to about 20 knots or so, which is below that 25 knot threshold for mini supercells. So we're kind of straddling that threshold throughout the entire lowest kilometer. And that makes me think that we may have a tendency toward more mini supercells in this environment. That would trump the seemingly high precipitation nature of the supercells. We see very short vectors up to the points above 6 kilometers there, meaning that we have very weak storm relative winds aloft, which, as we've talked about many times in this video, would favor high precipitation supercells. We do have some decent venting of the winds in the upper levels. You see some backing there in the mid levels of the hodograph. So that is one thing against high precipitation supercells, but what tends to trump all in this scenario is the tendency for mini supercells given weak low-level storm relative inflow. And in this environment, there were multiple tornado reports from mini supercells in central Minnesota on June 16th, 2025. And with this one, right off the bat, you can kind of tell this might be more of an HP storm mode. Our storm relative wind vectors are very short at 6 to 7 kilometers. It starts to stretch out a little bit from 8 to 9 kilometers there, but overall those 6 to 7 kilometer vectors are very, very short, very close to where the storm motion is. And we see that precipitation might be shunted right out ahead of the storm motion in the mid-levels. So your wind profile in this case would really favor high precipitation supercells. And this environment spawned a beastly high precipitation tornadic supercell in northern Kansas.
Remember to check out those links in the description below, and then watch another video.